Good evening, everyone. I hope you're enjoying your cake. It's really good. There's some more over the table. Um, okay, today I was going to talk about some of the research that I'm doing at the university where I'm teaching. And it's about solar-powered flight, and the picture is kind of giving it at night. There's not a lot of solar power. But what you see is actually the tip lights of the airplane. It's a long exposure, and the strobe light. We do very long flight times, like 32 hours. In this talk, I will introduce a little bit the aircraft, the motivation behind it. I hope I'm not going to go too technical, and then I will give you a little bit of an overview about where this stuff is going at this point from my lab, my research a little bit. I know it's not gliders, but most of the flying we've done was at glider ports in the area where we fly. I fly at Toronto Soaring Club, which is about an hour and a half northwest of Toronto, right in between three big lakes, Lake Erie, Lake Ontario, Lake Huron, and Georgian Bay. Lots of sea breeze, very flat area, but sometimes you can get some conversion lines. I try to spend as much time as possible there, like most of you probably. Unfortunately, I have to have a day job. So this is where my researchers group is located. We're calling ourselves the Applied Aerodynamics Laboratory of Flight, ALF. It used to be RALF, but the university used to be Ryerson University, but renamed itself 2 years ago because Mr. Ryerson had some baggage. The lab itself, it's pretty much downtown Toronto. It's an interesting campus. There are 40,000 students, like mixed in all the other traffic. There were the arrow points. In the basement, there's a wind tunnel, which I get to play with. But the work I've been doing was mostly motivated by some of my graduate students who, a few years ago, suggested that they could do some solar-powered flight. So they came to me in 2018 and said, like, we can build a small solar-powered aircraft that has batteries in the wing. And during the day, we use the solar cells to power the airplane, and also charge the batteries and then fly through the night and do this repeatedly. And this turned out into this project we call Creative Clean Renewable Energy Aerial Test Vehicle. It's somewhat of a tongue breaker, but you can see it here in flight nicely. It's taken from another drone. And just to give you an idea, the wingspan is roughly 20 feet. The aircraft itself weighs about 25 pounds, give or take. And we've moved quite a bit forward. And I will tell you a little bit more about this. So why use small UAVs with ultra-long flight durations? It's possible nowadays with the new technologies that we have available. We have better batteries and solar cells, and we also have sensors that are smaller and more power efficient that we can put on a smaller platform than a large one. And so new possibilities are opening up, especially also in the aircraft design. There are potential applications that I always tell people when I'm trying to sell this project to get funding. Airborne sensor platform is one big one, communication hubs. But what we wanted to do actually is a record flight, just become famous. The challenges, and this is purely academic or as an engineer, it's a new design space. The aircraft is small, it has to fit in a certain region, and it has to use a certain amount of power. Even more complicating is where we fly right now, we're limited to 400 feet above ground. I don't want to spend my career to get permission to fly higher. And the other challenge is power supply or power management ultimately. It's a new and exciting research area for innovative aircraft development like creative, and this is where I'm kind of been focusing my research lately. I should mention we're not the first ones. There are other long endurance airplanes. There's the RQ-4A, which has been flying for 30 hours. It does use fuel, but there's been the Atlantic Solar, which already like 15 years ago flew for 81 hours. It was a Swiss project out of ETH Zurich. And then more recently, 2 years ago, the Airbus Zephyr flew for 65 nonstop, which is pretty impressive. They didn't land in one piece, though. But we'll give it to them. Our aircraft, like I said, 2019 when we started building it, it's solar powered, 20-foot wingspan, about 28 pounds. We've flown it for about 100 hours, and the most noticeable flight is the 32-hour flight we did 2 years ago in July. And I have to say, it flies circles for 32 hours, and that's super exciting. Anyways, it's ultimately it's a hand-launched model airplane. If you look at it, you can sort of see the size. Um, but it's been the focus of my research, um, and it has been a very interesting design problem in general. It started out with a lot of weather data or sun data studying. NASA has and NOAA have a lot of data available. The colors mean more yellow, more sun, blue, less colorful. So Southern California, not surprisingly, is really ideal for this. Interestingly, northwestern Greenland also is quite ideal. It's because of the long days in the summertime. Um, Southern Ontario right here is not good. Nevertheless, we went along, charged ahead. We did some studies. Most of the technology we're using is pretty standard. The solar cells were ordered on Alibaba. The main things, these solar cells, they have to be flexible, so they can be fitted over the wing curvature, wing bending, and so on. It's about 90 lithium-ion batteries, about 4.5 kilograms. I forgot, it's about 10 pounds. The propulsion system is the model airplane builder will know these. And then the airfoil design was a custom design. So in aircraft design, the errors you do in the very beginning of a design phase are the ones that really get you in the long term. And when the students did the design, they did a design study for an airfoil with an optimizer. And I didn't pay attention. This is the airfoil, and there's some pressure distribution. And there was a couple of thoughts about this. So the idea is that the wing, you have the upper surface curved, and the solar cells could negotiate this curvature, but we were worried if we put on top of that, put the wing bending, that you get sort of like the chip effect, and it would then shatter. And so we designed an airfoil with 2 flat spots, and you pay a tremendous aerodynamic penalty with that. And if we had thought a little bit more about it, the curvature of the wing bending is actually not that dramatic. And you'll see later this design generation that got rid of this. Nevertheless, this data was used. We used some wind tunnel data from the propulsion system, some aerodynamic modeling, some solar modeling. We had a relatively complex model then. They used also aircraft input. And then using some of the meteorological data that was available, and then simulated about 10,000 different attempts of different configurations, and to see which one would succeed. So this graph shows the numbers of flights and number that they survived of these 10,000 flights, and we wanted to get right here into this range. In general, the simulation helped with identifying the final configuration. The wing design is pretty, as it comes, somewhat conventional, except that none of them had ever built a composites wing with molds, except for me. And on top of that, it happened also during the pandemic. The wing has a relatively high torsional and bending stiffness. It's a carbon fiber wing with some fiberglass to insulate the solar cells. We built a negative mold. So the wing, if you looked at the picture before, it was rectangular. And it's 3 panels, 3 rectangular panels. So we used the same mold for all 3 panels. And the molds you can see is our MDF board that we milled. Somebody made us available a large mill. And when we built the first wing, we learned a lot, and we built a second wing and indeed saved about 4.5 pounds while shaving off resin here and there. Let's see if I can start this. This is a time lapse of the layup process. That's me. This is everybody's masking up because we had to. These are the molds. They're going to lay up the molds, lay up the fabric here, and bring it over here. And we did this in a total of 12 times. So now they're putting the spark caps in. And now they're getting the vacuum bag ready. And That was like probably 8 hours. Yeah. And meanwhile, we were guests at the shop, this machine shop. They were like grinding stuff, banging stuff. It was super loud. It was a very interesting environment. Um, so this is just a look in the mold. You can see the mold is here. The edge of the mold is here. This is the fabric in the mold. After vacuum bagging, you can see little markings for cutouts to have some access to the wing part. Um, the ribs, the spar was pretty standard I-beam. The ribs are to hold the batteries. This all had to be prepared beforehand. Um, and then the molds are being joined. We were able to use the big overhead crane for that, which made it easier. Because these molds are really heavy. I'm trying to get rid of them right now, if anybody wants them. And so this is what the finished wing looks like, or one of the three panels. Again, these are access holes. They're not cut out yet. They're just marked there. The yellow stuff you see is a sandwich material. Again, debatable if it was the best choice, but we learn. And then we had our first flight in October 2019. It was like the worst day. It was windy and rainy, and I said, like, you guys are nuts. We're gonna crash. But it did work out, and we assembled the airplane in the morning. It actually turned out to be quite resilient towards the weather, which was helpful. There was lots of logistical issues. This is my old car, and this is the box held the airplane, the wings in it. Fortunately, a club member donated us a trailer, and that made it a little bit nicer the transport. We used a lot of the local airfields, glider ports, and private strips to do our flying. This is one of the examples. And here it goes off and then flies for hours to come. It's a good day. We should have gone soaring. In general, like I said, we did a lot of flights. In the beginning, flying for 2 hours was quite the accomplishment. We thought later on, if we didn't fly 5 hours or longer, it was really a short flight. We got a lot of, we did a lot of experiments. We did a lot of measuring of power needs of the aircraft. We got a lot of data related to the solar input with the solar cells register. And we also recorded a lot of information about the aircraft states. And this data has been really invaluable for doing research studies, all kinds of for optimizations and other design studies. And I want to highlight this a little bit. Lots of data collected and ready for the next round of improvements. So in particular, with the flight test data, I want to just kind of highlight this. We measured the power required to fly it. Usually you guys are, or we as glider pilots, we're interested in sync rates or LFD curves. That's the equivalent for a powered airplane. We look a little bit on the propulsion optimization. There's some solar power modeling that was done. And then flight path optimization. I'll go over to this. This is a result from one of my students' master's thesis. What he did is, okay, so gliders are usually measured. The EDA fleet has a Discus 2C where they know the performance quite well, and then they usually fly it next to the other glider and compare the relative performance. Unfortunately, we don't have calibration airplanes like this, but we can't really easily do like altitude steppings like Dick Johnson would do. One of the really big challenges is because of the low wing loadings of the aircraft, any atmospheric motion really skews the data. And so the data you see there is actually from an energy method where the aircraft starts at high speeds. No, actually it started at low speeds and would accelerate. We knew the performance of the propulsion system, and then we could back out the drag. What you see is here on the vertical axis is the lift coefficient, fast flight, slow flight, and then here the drag coefficient. And you can see the scattering like crazy, including negative drags, which means we hit updrafts essentially. But the idea is that if you do it often enough, you get a statistical mean. And that was the main idea of this process. Again, low wing loading poses a challenge in free flight experiments for these small aircraft. And that's true for all of them, not just for solar-powered ones. We put a lot of work into the propulsion system. So in general, just an idea for higher efficiencies, the propellers usually like to turn slowly, but motors, electric motors, for their higher efficiency, need to like to turn fast. So you have these counteracting design constraints. Also, we needed enough thrust for takeoff, even though it's hand launched. There was a limit to what our hand launchers were able to do. One literally got his shoulder yanked out at some point. And then for the loiter speed around 20 knots, we wanted to minimize the power required, or the minimum power that the losses at the propulsion system. In general, and this is true for any aircraft design, propeller, motor, airframe, have different maximum efficiency points and have to be tailored to each other. And this is one of these attempts. What it shows is on the vertical axis, the maximal overall efficiency of the propulsion system, that is motor and propeller together, plotted over the propeller diameter for these lines are different propellers. Each color denotes having the same twist, pitch per diameter distribution. Anyways, the diameter gets larger this way, the pitch goes up this way and then goes down again. The main thing to take away, the largest diameter is not always the best. This is the one we were using. This is the theoretical maximum. And then there in the catalog, these are the ones you can actually buy. And so these are these trade studies you do then when you have the data. A large propeller diameter and pitch to diameter ratio do not guarantee better overall efficiency. And that's pretty obvious for anybody who's done model airplane flying. Right. The other thing which is interesting, so we're trying to fly through the night, and so the night's pretty straightforward. You just fly minimum power required. But then the problem is like in the morning, early in the morning, or late in the afternoon, when the sun is low, you need to get flying the constant bank angle might not help. You might want to bank steeper. And the idea is the more perpendicular the sun rays hit the solar cells, the more solar power you can get. Of course, this is kind of counter to if you fly steeper, you need more power to maintain flight. And so there's a nice trade study. Again, we had the data where we looked at, we measured these gray dots are all like solar data recorded during a flight. And it changes because the aircraft banks in and out of the wind. It flies the circle over the ground and has to adjust for the wind. The blue line is the average to that, and then the model that we developed of using is the red line. There's a small offset, but otherwise it fits quite well. And overall, then the solar power that's being collected minus the power that's required leads to a charge of the battery. This becomes a little bit more complicated when you have lots of wind, and I tried to show this with this little cartoon. If the wind's blowing from the upper left and the sun stands to the right, the airplane, the question is, do you fly clockwise or counterclockwise? If you fly clockwise, you spend more time in the upwind part where the sun can affect the solar cells. If you fly counterclockwise, you have more bank angle on this side, but you spend more time at the unfavorable bank angle towards the sun. So we spent quite a bit of time trying to figure out is left or right better with different winds, and there are some rules. But overall, wind matters less than we expected. We're not quite there yet. One big study is, again, I mentioned Southern Ontario is not the best location. If we have lots of clouds, we have a lot of wind, we have a lot of rain too. There's some other advances that come, that's better batteries. Battery technology has really tremendously improved in the last 4 years, and it keeps improving. And then we're exploring new flight strategies. Kind of like speed to fly, we do in gliders. The problem is we want to stay up longer. We don't want to fly far. So that changes a little bit the rules. We also have this 400 foot above ground level limit in altitude, and the ground, as that's the other limit. But one thing which we've actually been exploring, and this is something outside of the soaring domain a little bit, is you guys are pretty much familiar with the morning inversion, doing the radiation at night, and you have an inversion that climbs up. And then we have this effect that close to the ground there's no wind, and then above the inversion there's quite a bit of wind. So we have quite a bit of wind shear. And you might have heard about dynamic soaring. Dynamic soaring is where you crazily dive in and out of these wind shears. We don't want to do this. We call it not so dynamic soaring, where you just kind of gently kind of dip in and out. And our numbers at least indicate that you can easily save 5 to 10% in power, which would be significant for us. Yeah, so much about creative. I want to take it to the next step. This is the next generation. Like I mentioned, it was a group of students, graduate students of mine, who came up and said, like, hey, we want to do this project. I had funding. I told them, run with this. They all graduated, or most of them, and then started their own company with this aircraft, which you just saw catapulted there. And they're trying to commercialize it. It's a little bit smaller. It has only a 17-foot wingspan. It's heavier. It's almost 50 pounds. It uses airfoil that works decently, and it was redesigned airfoil. And they use it for a lot of wildlife observations, studies. The advantage of the aircraft is because it's electric propulsion, it's really quiet. When you're underneath of it and it flies about a couple hundred feet above you, you can't hear it. So the advantage there is that it doesn't disturb the animals. It's very little intrusion. The solar cells have the advantage. The surveying, again, I got some videos there in a little bit. The surveying is usually done in the winter time. And in the winter time in Canada, it gets cold. And the batteries usually lose their performance in the cold. But the solar cells work really well. So without solar cells, they could fly for 3 hours. With solar cells, they can fly easily 8 hours, which means one takeoff per day. And then they get footage like this. They fly around, look at the deer, and other animals, and try to classify them. And this is for different territorial of provincial governments in Canada. This is footage from Manitoba, a campaign in Manitoba. And the thing which is amazing is they have lots and lots of this footage where the animals don't seem to be bothered by the presence of the aircraft at all. Now, it's a little bit hard to find them, and so what they do is actually they use infrared cameras, heat-seeking, and you can see, in that case, moose quite easily. And when they identify these hotspots, then they change over to the RGB, or visual light camera, and try to identify the species and the gender and whatever biologists want to know. Yeah. And I find it pretty amazing. Again, the animal does not seem to be bothered by it much. Also, I want to point out that the longitude latitudes are being blurred out on purpose. They insisted on that, so hunters can't take advantage of that. This is a typical mission they did. That was in February 2023, but they did a similar one this year in February. They surveyed about 320,000 acres. I looked it up. That's half the size of Rhode Island. Again, the solar capabilities allowed for single flight. What you see in the picture are the transects, basically the flight paths they flew along to survey the entire area. What they would do, they would take off one place, fly a certain area, then reposition the aircraft and the ground vehicle to another place, to a different area, and move on, for so on and on. The red parts were farms where they had to stay away. But so it's super convenient. Once it's airborne, it's airborne. The only restriction right now, we can't fly beyond visual line of sight. That means they have to stay within 2 kilometers, about 1.5 miles. But they did a total of 80 hours, flight hours, on average 7 flight hours per day, roughly. 7,400 acres per hour. And again, it's two persons, one operating observing the aircraft, the other one observing the cameras and counting animals. And then you see also something like this. The animal world is not necessarily friendly with each other. These are mule deer chasing off whitetails. They don't like each other apparently. And the next video is my favorite. There's a fox. That's the only animal that sees the airplane. And Mark, here comes you. Mark said he was going to bark. Anyways, so that was the only time in video where we actually saw that the animals took notice of the aircraft. This is a typical landing. This was last fall, a campaign on Point Pelee. Point Pelee is a peninsula that reaches into Lake Erie. It's literally the most southern point of Canada, and it's a national park, and there's quite a deer population, and so they assessed how many deer were there, and based on this, there was deer control being performed. Last March, they did a campaign in the Yukon. You can see there the airplane being catapult launched from a frozen lake, and the idea was to monitor and takes off and then was gone for 3 hours. This was just a pure battery version, and the idea was to survey for elk up here, and also caribou. So caribou are an interesting thing. It's like in Canada, they are the food source for several groups, especially in the Canadian North. Unfortunately, the animals are being are endangered, and we don't quite understand why. And so there's a potential that we're hoping to provide more insight. Why do these animals get decimated by wolves or whatever caused them? Again, the non-intrusiveness of this relatively quiet aircraft is a true advantage. The Yukon government liked this project so much from last March that actually the group is going up there again next week Friday to survey along the highway for animals, 2 kilometers on either side in November, and the days are really short there. With this, I'm actually getting towards the end of my talk, and want to kind of wrap it up. It was a really exciting project, and it really formed my research direction. There are some very interesting problems, design problems, operational problems, planning problems. There's more to come. Again, I think small UAVs have a real potential of becoming some interesting tools. The solar cells, batteries, and electronics get better and smaller and less dollar hungry. I think there's a sunny future. And I do have to say, this work would not be possible without the help of the Soaring community in Southern Ontario, because we're able to use all their fields for takeoffs and landings and tests often. And with this, I'm getting to the end of my talk and some pictures to cool everyone down. Thank you so much. Any?
My name is Pete. The question is, the batteries don't have that infinite amount of lifespan on them. They have a cycling problem. And once you seal them in those wings, how hard is it to get those batteries out? Do you sacrifice the wings? Is the wing done for what?
Okay, I didn't specify this, but the batteries can actually be taken out of the wings. They're kind of like you have water bags sometimes in gliders. You can take them out through the root. Okay. But good point. Yeah, they don't have an infinite lifetime. Any other questions? Yeah.
I didn't quite get who flies this machine. Is this all on autopilot?
It is a kind of mix. So landing and takeoff is usually manually, assisted by autopilot. And then once it's on a mission, it flies from waypoint to waypoint until an animal is being detected. And then it's being taken out of autopilot, and then they circle back if needed. Okay.
I'm just curious, did you discuss optimizing the power used by considering an alternate takeoff scheme? Like like the gliders using a winch launch or an arrow tow to save a little electric efficiency?
We've not really considered, because once it's airborne, it's airborne. And so far, with the creative, the smaller one, it was light enough that two people can easily like haul it into the air. Now with the I did mention it, but the newer one, it's called George, mainly because we didn't come up with a better name. That one is catapult launch because it's much heavier and yeah.
Do you have plans to fly it higher, and what are the regulatory challenges with the airspace?
So in general, just like in the US, you need to have ADS-B or something like this, and you need to be able to observe it somewhere. There was, however, the chance there's an airspace in Alberta where the New Medicine had, where they have an airspace that's reserved for UAVs. They were going to use it, but it didn't quite pan out. To be honest, we considered it for a while to use altitude as well, but Transport Canada is there to serve the people. No, that is super helpful, but in that case, I would be scared too. And this is not where I wanted to put my effort in my career.
So I got confused a little bit. You built the wings in 2000 or 2001 during COVID, but the first flight was in 2019. So did you have a second airplane?
I might have been a little bit imprecise there. The first wings were built in 2019 and flew in 2019. And then in 2019 through 2020, right through actually 2020, 2021, during the pandemic, we built a second wing. Yeah. Can I go back to my dessert? Oh,
So in your photo, you show flying in a circle. Is that required? Because the reason is, if you do a figure eight, and say you got a 10-knot wind, you're flying perpendicular to the wind, you're going 20 knots, you got a 30-degree crab angle. So now you got to turn 120 degrees to go back the other way, so you spend much less time turning, so you might be more efficient.
that's a good point. We're a little constrained that we're staying within 2 kilometers in general. So when they do the surveying mission, they do plan them so that they fly perpendicular to the wind. So you don't have to fly in and out of the wind. For the creative, the long endurance one, we just did circle mostly. But, yeah.
What kind of camera were you shooting with?
Oh boy. It's an expensive one. It's a dual camera with like infrared IR and RGB. I think it's mostly digital zoom. It does have a what do you call it? A swivel, a gimbal. Thank you. Yeah. And it needs to be retracted for landing. Otherwise, you got to buy a new one. So there are also these learning effects. So UAVs to a certain extent are a little bit of a wild west. This is why I don't blame the FAA or Transport Canada of being somewhat restrictive. There were some learning experience where new equipment was introduced that required some changing of the codes, and that caused for some unusual flight conditions, including a crash, which then gave me a wind tunnel model. So, so we have all these regulations and procedures in gliding, and they don't exist for small UAVs or large UAVs at this point. And that's something just to keep in mind. Like technically, there's a lot of things more possible, but we should be careful.
What chemistry batteries did you use, and did you have issues with cold weather affecting the batteries?
So they're regular lithium ion. Oh, okay, I'm gonna punt that down to my students. But they are affected by cold. So, like I said, like in the cold of Manitoba, they fly for 3 hours. Get 3 hours endurance out of this. No heating. That's the next step. We're looking into this actually. So the other thing, which is an interesting thing, or what we encountered is icing. The problem is you're not on board of the aircraft. You don't even know what happens. And so and icing on small airplanes happens really fast because of the low pressures that these wings produce. The water drops are not being deviated as fast, necessarily as much. And so you accrue quite a bit of ice. I got some. You can see there the leading edge of the wing. There was after one flight where they got into, there was some ground fog. And the only thing they knew was that the power requirement went up. And so a lot of effort there. It's a typical Canadian problem, I think. But the idea is to come up with some sensors that can tell you get close to icing conditions, and then you just kind of return. All right. Any other questions? Thank you, everyone.